Hello. Hello, everyone. So, thank you for coming and welcome to this session. We have Bogdan Arsintescu. Arsintescu. I always mix. Sorry about that. So he's now with Microsoft. He's leading the Fabric Graph at Microsoft. He used to work for LinkedIn, being one of the leaders of the effort, the graph systems effort. He accumulates a lot of knowledge from his having worked both for Google as well, LinkedIn and then Microsoft. And I think that he can give us a lot of experience, that it's something that you never get out of just a simple talk, but out of the way people explains and the way they are able to express that. So thank you very much for being with us, and it's your time.
Oops. I don't know if I'm wearing this well, but this is going to have to do. So thank you so much for coming to this tech talk. I was talking to a friend the other day, and they understood that I'm doing a TED talk. And you will recognize that I put these sentences one after the other so that they edit the video and pretend that I did a TED talk. So we're going to talk about graphs today and graph systems. They are different than relational databases. They have different applications. This talk in particular is not going to be a lot of technical depth. It's going to be more technical breadth about how we arrived at the ideas. I have another talk that you can find on YouTube about how we designed the technology at LinkedIn, how did we scale it. But this is going to be mostly about the taxonomy of scale. How do we think about scale in graph systems? What are the dimensions in which we look, and how do we make decisions? Then I'm going to talk about modeling graphs over the entire data estate. Corporations have huge amounts of data, and they're trying to figure out how to extract business logic out of their data. So the way they do, they model graphs, connections, relationships between these data sources, and how you can do it efficiently. I will touch a little bit snarkily over the religious wars in the graph database community between property graphs and RDF. And it's all about how you look at it. In the end, is the same kind of relationship. It's all graphs. A little bit in the end about graph workloads in the graph system. So this is touching about my work at Microsoft. How do you structure products around graph? When you're offering somebody a set of tools, what are the right tools that you're offering them? And in the last couple of slides, what is the master plan? What are all the things that we're trying to do in offering graph system for the enterprise? So first, about scale. When we have graphs, the first thing that you're thinking is you have large graphs and you have small graphs. Large graphs are insights across multiple large silos. If you take LinkedIn as a business, LinkedIn has a table of connections between members. This person is connected to that person. They have, for each person, they have positions. I worked at company A, I worked at company B. I am contributing to this conference, I'm contributing to that conference. I went to school A, to school B. All these silos are in different tables. All this data is partitioned in different places in the organization, but when you are bringing LinkedIn up, you want to see a profile that shows a good business model, a good business logic about over this data. What is that business logic? It's the semantic. Connections are one semantic, jobs are another semantic, positions, which is the job history, is another semantic. So you want to layer that semantic model over the data from different tables and create a graph that you can navigate. If you look at the LinkedIn pages, they're each a different walk through that graph. They're a traversal of that community. Another example that you can relate to, if you look at the knowledge panels, whether in Bing or at Google, a knowledge panel is the right-hand side of the search page, that if you search for a personality, if you search for Lady Gaga or Taylor Swift or Barack Obama or Donald Trump, please don't, then you can see a structured page with information that is coming from understanding who that person is. So for a musician, you get the information about the person, their relationship. You get the information about their music, and that's a different ontology. You get information about movies that they played in. You know, different ontologies layer on each other. It's structured as a page of information. It looks like a Wikipedia page. It comes from a graph. It comes from a knowledge graph. In both cases, in Microsoft, Satori was the name of the graph. And then it was the Google Knowledge Graph that started around 2010. So these are the large case studies. Another case study for large graphs are customer 360 graphs. So if you have a bank that is giving you an account and it gives you loans for cars and mortgages for houses, the moment you call their number, they will look at your profile by accessing data from different tables. They create a customer 360 view of your financial situation, your calls, the tickets that you filed, all of it is shown in one given page. Internet of Things is the same thing. You know, you want to monitor operations on a factory, you model that the data that is coming from the sensors and the factory produces as a semantic. You look at it and you're trying to predict things, or you're trying to figure out how do you do repairs. I'll give you an example of, British Petroleum or any large petroleum corporation. They usually have 3 different arms. One of them is extraction, so it's how you get the oil from the ground to the refinery. Another one is the extraction itself and the distribution. How do you get from the tanker, how do you get it to the trucks that are carrying? And the third part is from the trucks to the gas station where you're getting the gas. Now, that is modeled as a graph, you know, how this data flows in the systems. And then imagine that there's a storm, there's a tornado happening there's a hurricane happening in the ocean. You will have boats that will have to go to different places. You will have refineries that will have to hire people because they will have to slow production in one place. People will be displaced in one place for probably months, and they will have to move data from somewhere else. And trucks will have to take that gasoline and take it to the same gas stations. And when that happens, you will have to compute the perturbation that the storm is bringing into the entire system and propagate that wave and understand how to adapt your operations to the disruption that the storm is coming, and how quickly can you rebuild all that after the storm has gone. So all that is the Internet of Things, is a digital twin of reality. You have the operations, you model a graph around it, you can reason about it. Fraud detection is the same way. Or you have small graphs, and Larry here has worked on embedded application, right? So you have compute at the edge, which is getting the part of the graph that the device or the person looking at their phone needs, and you need to overlay personalization on top of it. So these are, the kinds of large and small graphs that you need to operate on. So you need to design separate systems for small and large graphs. The query shape, what is the shape, how much of the graph are you touching with the query? When you're trying to extract information, are you just in a vicinity of a couple of stars? You just need a constellation, a small graph traversal in a vicinity, or you're trying to catalog the data that you have in the entire universe of your graph, and you're saying, oh, these are this kind of constellations that I have. So that's more of an analytical workload. Or you're doing data enrichment. You're looking at the entire universe, and I'm saying, I think I detect this kind of pattern, this kind of community, this kind of grouping, and put the data together. So this is another type of way in which you're looking at your domain, and you're saying, this is the kind of query shape that I will apply. For each of these query shape, the kind of algorithms and the kind of systems that you need to build are going to be different. The last one that I will discuss is the lifespan of the graph. Are you doing an ephemeral graph or are you doing a permanent graph? So for ephemeral workloads, you have on-demand index creation. You have all the tables where you have exabytes of data and you just extract a small vicinity and you put it together and you consume it and then you let it go. This is also called serverless computing, right? So you don't own the server. You just bring the data into a compute environment, you run your workload and you let it go. On the permanent workloads is the whole graph is required all the time. And this is, if you look at LinkedIn, the way we've done the backends, the database that is holding LinkedIn, that is a permanent graph. It has to work the entire year, and as a user, it should never be down, right? It should work as a utility. It has to always be present. In that case, you have repairability, you have replication, you're not using the compute efficiently because you have to provide services for availability, 4 nines of availability. So it has to be 99.99% of the year, it has to be there. You won't want to pick up your phone and the service not working. So the personas that are consuming this, I have this on the slide, you know, on the ephemeral lifespan. As an analyst, I prepare a logistic report every other Friday. So for the rest of the time, if you're keeping that compute occupied with petabytes of data, you're wasting money. As a driver, I check travel regularly on the permanent workload. When you're checking location data, you want the data to be fresh. You want it to be, you know, 5 minutes old, 10 minutes old, and you want it always there. You cannot just prepare 2 weeks in advance that you're going to have a trip. So when you put it all together, then you start talking about different kinds of systems for different kind of workloads, right? And that I color-coded the circles there. So on one dimension, you have latency, right? So you have fast system, fast response time, and slow response time. So fast means milliseconds or tens of milliseconds or hundreds of milliseconds. I'll give you a turn within 100 milliseconds. Anybody that's waiting for more than 100 milliseconds gets bored, blames it on Google because it's not happening fast enough. Then you have small size, large size on the second axis, and you know, how much of the graph are you building. And for lack of a better graphic, I put a you know, colorless Rubik cube there. So if you have systems that are in the yellow circle where you're touching a lot of the graph, it doesn't have to be extremely fast, and the graphs are extremely large, then you have what is called online analytics system. So these are things where you're trying to catalog the graph. So these are the constellation things, if you remember the imagery of that. Then you have transactional processing, where the graphs might be either small or large, but you have to do something very fast. It's an operational workload. The user is waiting for the data. And that's where you can start playing with is this ephemeral, is this permanent, right? So if it's ephemeral, then the pressure on your designing the system is going to be how fast can you bring the data in? The data is small, so you can return the query very fast no matter what. But how fast can you build it? How fast can you tear it down? If the data is large and you need low latency responses, then like in the LinkedIn example, you need to keep the system alive all the time, but you have to distribute it because it's not going to fit in the memory of a single machine. You need a distributed system. And then in the third example, you have high performance computing. These are systems where you're touching, everything has to work. You're touching the entire graph. The data is huge, so you definitely have to parallelize it. You have to analyze the entire data set over a long period of time. They're not very fast. And these are systems built for data scientists, so people that are just crunching through all the numbers and they want to find systematic results over that data. So these people have a hunch, these people have a mission, these people want to do science, right? So these are the 3 different kind of personas that you're building for in the graph domain, right? Why am I doing all this? You know, think about the problems that you're solving. The problems that are solving, you have to solve it for the right persona, for the right size, and you have to understand, you have to have a taxonomy in which you're talking about what you're doing. I had a boss at LinkedIn who was telling me that that everybody in his organization has to explain what are they doing in a elevator ride that's 3 floors. If you don't do it, you're gone. You don't get the job. So case study, LinkedIn. So this is more about the system that I built between 2017 and this year at LinkedIn. We're taking the same technology to Microsoft. You can find more in-depth information about this in another video that I've done a couple of years back for, there is one at VLDB and another one at I don't remember what conference it was. Dub, I think. This is a scale out, low latency. You don't have any replication within a given cluster. So the way you achieve the availability is you replicate, you have multiple copies of this. So if one of this shard fails, if one of this hardware just dies, it burns out because you're running it at 90% CPU, so it gets very hot. Then what happens is you have to bring another one of these machines. You have to bring a copy of the data from one of its peers that has the same slice of the data, the same slice of the pie. You have to bring it from somewhere else, reinstall it, and bring it back up. This system is being restored in somewhere between 6 and 10 minutes if one machine fails. So that's how long it takes for all these operations to happen. But in those 10 minutes, you have to have another replica that takes the traffic that was coming from this machine. So if you compute what 4 nines is, it's minutes within a year. 5 nines is seconds within a year. All right, so if you try to make a system that works towards that, then you're lowering your compute, you're creating more replicas such that you can repair, you have time to repair it, right? So you're masking your hardware failures by lowering the consumption of the CPU. How do you do experimentation? We have data that is coming from sources of truth, and you have ETL dumps of sources of truth. You have change feeds, and these are streaming systems. In LinkedIn, the data was being rebuilt every week. It was being rebuilt every week because we needed to process GDPR requests of deleting data permanently in the index. The index was a log-based index. Anybody that studied the theory, it means that knows that those indexes keep the data from the beginning of time. The European Parliament don't want you to keep the data from the beginning of time, so you have to compress. If you compress, the system becomes more complicated. If you rebuild the image, the system can still be simple. So that's an exercise in how do you create a procedure to do the updates while keeping the system still simple. Okay, enough about scale. Graph models over the data estate. And this is where the database community is trying to create a story that isn't there, right? So you have 2 tables, and I only have the headers of the tables that have one ID that has a foreign key in another table, and this one has another key as its ID. The way you create a graph is these are the relation, and all the other columns are properties of that ID, right? So imagine employee ID, last name, first name, date of birth, date of hire, right? And this one can be company, title, employee ID, and some other things about the company. That's how relational databases work, right? So the companies are very good at creating these tables that, you all have created an Excel spreadsheet, so you know how those things work. If you want to look at this data as a graph, what you do, you're actually creating a Scrabble-like structure of those 2 things, and you're saying, oh, this key is a foreign key in the other table, so that's my connection in the graph. The database community, or the graph database community, has created the idea of labeled property graphs. So you have one set of vertices, which are IDs, another set of vertices, which are keys. There are edges between them, and everything is a property. Another part of the graph database community has created another structure where you have everything is a node. So you have the ID and the key that you recognize from the other tables, and the other the properties are also indexed. Is there any fundamental difference between them? No, it's just representation. There is no fundamental difference between a property graph and the RDF graph. The other ones are RDF or triples graphs. Then the way you index it, the way you use the memory. So when I got into the graph community, I came from VLSI, and for a couple of years I was trying to understand, is there a difference? Because people were making it such a big deal, and there wasn't one. And then, you know, there are even more complicated words in the graph community. Ontology, what is a taxonomy? What is LPG? What is RDF? So in a LPG labeled property graph, labels are not indexed. It saves a lot of memory. So your graph becomes smaller. You can take all the properties and put them outside and do just graph compute in a smaller footprint. So if you just want to traverse a few types of relationship and everything else is decoration, then you can use that kind of model. These are similar to what 20 years ago was object-oriented databases. It is similar to the NoSQL key value store structures that are distributing data by creating a hash table of keys with all of them with pages with documents of information. On the other side of the slide, the triples are all much more uniform. They're all in the subject predicate object structure. Bogdan presents UPC, right? So that's one triple. Bogdan works at Microsoft, right? That's another triple. If the data is, if the schema is defined without much thought about logic, then it's a taxonomy. It's just a schema that you define. If you have the intent to reason, to apply logic over that schema, to think in logical terms, then you need to use an ontology. And I have some details on what ontologies are in the next slide. And then RDF and OWL are ways to harmonize this ontology and this semantic of the data over different graphs in different places. So RDF is a way to describe all the ontologies in the world in a natural way. So everybody talks about people or actors or friend of a friend in a similar way. These are very good for collaboration. These are very good for exchanging data or self-explaining what the data is. Neither of these n-ary relationships are hard to describe. So I'll give an example. So if you look at my work history, if you want to describe a job by just a relationship between me and the company, you can't model the fact that I worked at Cadence twice. So the only way to describe that relationship is to mediate it by time, to say, Bogdan worked at Cadence starting in, I'm going to date myself, 1998, and Bogdan worked at Cadence starting in 2004, because I quit the company, I came back, right? That triple of information has two edges. One of them is connection between me and the company, and the other one is start time for that thing, or when somebody started working somewhere, or somebody started a marriage. So there are many relationships that are mediated that are n-ary, and the binary relationship, the subject predicate object, is not enough to describe the entire relationship. So there are different ways of doing this. Many databases are creating artificial nodes that are holding that identity, and they have edges across them. LPGs are putting properties on the edges, right? So the edge between me and Cadence, there are two edges. One of them has one date and another one has another date. So, in summary, what is a GraphDB? And, I like the definition from Cod, because he's a parent of relational databases, and he's the one that best described the graph databases. It's a database in which all joins are pre-materialized, right? So that's the relational view of it. In graph terms, it's a index of the data in which relationships and not the tables are, right? So graph databases are all about relationship. Relational databases are not about relationships, oddly. So you have a schema, which is an ER diagram that tells you which joins will be pre-materialized and which indices are to be built. You have the graph, and again, we're going back to the taxonomy of scale. You have to figure out what is the useful portion of the data from the original tables that you're going to index. And then, which kind of model are you going to use? It depends exactly on the application that you're going to do. And then a database system is, the model of computation that you're building around your data to scale up and scale out. Scale up is something where if you need twice the size of the database, you give it twice the size of memory. So, if you need 20 times, then you give it 20 times. So then you get to go buy a computer that has 1 petabyte of RAM. It's a little bit expensive. Scale out is solving that problem by parallelizing, by saying, if I need twice the amount of data, I'll get 2 computers and figure out how to distribute the computation between them, right? So this is what you've seen in the last 20 years with MapReduce and distributed systems. This is why distributed systems matter. I'm going to plug, your teachers ask me to plug this thing. Go to do a distributed systems class. And then how do you query this data? For local traversals, you can use a scatter-gather distributed system. For analytics, if you imagine what a scatter-gather does, it collects all the data that it needs in one single place. Well, you're getting into the scale-out problem. You need a lot of memory to process that. If you don't have a lot of memory, then what you do is you shuffle it to disk, and you bring the information back in a different way. So these are different patterns of execution in graph databases. Now, there are graphs that are extremely large. Right? And you're only interested in one community in this graph. What do you do about that? Well, you can isolate it. You can put it into a smaller system, and you can look at it, but you can look at it even in more details. And now you start zooming in. So again, this is another way of practicality in what do you do about the data? What do you need to analyze? What is the data that you have to look at? And you have graph models that can define namespaces in the community. Again, I'll go to the example with LinkedIn. If you only need jobs, you have a page that just looks at jobs. If you have connections, then you have profiles. If you have activity, then you have a page that looks at your social feed, the communications that your peers have done. So that's a way to namespace the part of the graph that you're looking at. Algorithms can be used to identify communities based on objective functions. So if you want to detect whether somebody is part of a given community, you can run various algorithms. If you want to detect fraud, you can look for patterns of fraud. Every activity, thieves are talking to each other, in case you haven't heard that. So they copy how they work. There are very few thieves are creative. They just repeat the same thing over and over. Those are patterns. You can detect them with algorithms. And humans, in the end, can customize this partition. So, the question for all this, how do you scale down a graph? How do you define a system that works for your graph? Is ask yourself, what is useful, right? And that's the part that you have to bring in your computation. Graph workloads, right? So now we're getting the scale and the schema and the graph neighborhood that we want to bring. And we're just defining what are the kinds of systems that we want to build. And if you look at the cloud systems, everybody is selling systems in these 3 categories, right? So there's analysts that need to process the data. You need to give them analytics. There are transactional, so there are developers that want to bring their data into an applications and hand it to their user. Those are transactional system. And high-performance compute is ways to use the computer, the compute, the network, the disk, with a maximum throughput to extract new information in a systematic way. Again, how do you focus on the right vicinity? You use the appropriate semantic and use the appropriate scope. Right? So these are, going back to what we talked earlier in the discussion. And then now, do you need knowledge graphs or do you need just a knowledge base? This is about how rigorous your schema is. If you're just talking about a collection of facts that you just want to analyze, you just need a knowledge base. You don't care that much of the types and the subject and the predicates that you're using. A knowledge graph, on the other hand, is knowledge base, so it's that thing where the schema and the predicates are an ontology. So I'll give you an example of an ontology. If you're talking about administration, right? So if I'm a user and I'm saying I need a passport, right? You need an ontology to describe who gives people a passport, right? And I'll use United States as an example. If you're abroad, a consulate gives you a passport. If you're in the United States, post office gives you a passport. So the answer is a logical traversal of the schema. So when Bogdan is in the United States and asks for a passport, then you use the ontology for the local domain and you send them to a post office. When they are abroad, you send them to a consulate. Right? So that's a logical traversal of the data. So ontology then is a description of the data, structure and classes, properties and relationship in a domain of knowledge. And this is linguistics and reasoning, because you want to apply reason. You want to apply logic to figure out what is the query that you're going to write. So the query is, I need a passport. The transformation of the query with the ontology relates to the location modeling and to the organization of the government modeling and so on and so forth. And last but not least, taxonomy is about classifying data into categories. So most people that are in this domain, they all talk about knowledge graphs and ontologies, but in the end, what they do is just a simple schema with taxonomy, because they never apply reasoning over the data. They handwrite the queries. So the master plan, how do all these things come together? You have to think about the personas that you're designing for. You have to find the right tool for each task. And think of it this way. A Swiss Army knife is very useful for nothing. I think all of us have a knife like that. It's somewhere in a drawer. It's not very good as a knife. It's not very good as a screwdriver. I've used it to uncork a bottle of wine, so I think that's the main purpose for, it's very successful at that. But other than that, it's not a good tool, right? If I need a knife, then I need a sharp knife, right? If I'm filleting a fish, then I need an even sharper, thinner knife. If I pare an apple, if I cut an apple, then I need a shorter knife with a different kind of blade, because the big fish knife is not going to help. So there are different tools. If people are going to tell you that they solve everything with a tool, as an engineer, imagine a Swiss Army knife. No, they won't. And then in the tools that you're developing, you have to allow interaction with a diverse platform that has other tools that are not yours. You don't have to build everything. You just have to build what you're good at. Because if you're doing knives, you're not going to be very good at corkscrews. Maybe you are if you're WMF, but in general, let's say as an engineer, you're going to be good at one thing. And each persona uses a variety of tools, and they will move from one tool to another to achieve the goal that they have. And there is no single tool, there is no single pot that allows a cook to cook everything. So they need different tools. And the more things change, the more they stay the same. So as an engineer, you will discover that what you're doing is obsolete 3 years from now. Don't worry about it. That's what job security is. That's what keeps us employed until retirement. There's always a job for us. As an engineer, and this is the message for all of you, you have to build the right abstraction. And in the graph domain, what are the users doing? It's not just in the graph domain, it's in the data science domain. They're modeling the data, they're gathering insights, they enrich the data by creating new data, they're structuring it, right? So they're discovering things, and they're looking at the set of stars and they're saying, oh, this is Orion, it's a constellation. And then they iterate. They do it again and again and again. And over time, they become more sophisticated about it. And then they build an application that they put in the hand of the user. And then they want to experiment. What if I change this application? What if I make it more sophisticated? And they iterate over that. So this is the message that I want to leave you with. And this was what the entire talk was about. You have to figure out who you are, right? What do you want to build? If you want to build minivans, this is the factory you're going to be in. If you want to build or service Formula One cars, that's going to be the kind of engineer that you're going to be. The systems that you're building are the same. You have to build the right system for the right set of users. There is no single, that's why you're not seeing minivans in Formula Ones. Thank you. I didn't want to do any plugs in that. So I am part of Microsoft. The reason why I'm here is because with my colleagues in the back there, we're hiring. We're trying to hire 25 systems engineers in Barcelona this year and probably more next year. I'm not going to put a number because it's hard to put numbers on that. I'm hiring for the graph team. I look for graph experts. We're looking for database experts. We're looking for system and storage experts. At every level in their career. So, expertise comes from people that have done good classes. Expertise comes from people that have worked 20 years in a domain. So it's not just, you don't have to be a rocket scientist. We're not looking for rocket scientists. And so that's the reason why I'm here. So now questions, anything that you would like to ask? Yes.
To ask, you said that the graph database used in LinkedIn, it was developed within LinkedIn, right? And now you said that you wanted to generalize it to use it as well in Microsoft, right? Is there any plan to make it open source or like to make it more generic even? Or rather, the question could also be framed as how generic is that graph database? Thank you.
So philosophically, company open source things that are not their core domain. Right? So if something is not very important, that's not how they make money. They will open source something, right? So we will figure out what we want to open source and not. That's not my, that's not my decision. Do we want to open source what has been done at LinkedIn? Is not necessary. There are many other indices that exist out there that are doing similar things. There was a paper 3 or 4 years ago at Sigmod from University of Amherst that was describing an index, and it was open source. FUBU from University of Waterloo is another graph index that is open source. So creating another project in the same space doesn't help. So figuring out maybe we contribute to one of those makes more sense than not. There was another part of your question, how easy it is to generalize. We have a distributed index, and that's the beauty of that. So the database at LinkedIn is a log-based structure, so it's append at the end. It has a hash table in front of it because graph workloads are random access. And we know how to run distributed query execution on it. We don't yet know how to do analytics on it and algorithms. So that's the part that we will collaborate with them. They're still our colleagues, right? So LinkedIn and Microsoft are one company. So we will work on that code together, but we're going to do, LinkedIn is not running that project. We're going to develop that project. And it's going to be in Barcelona. That's shameless plug. Thank you.
Thank you.
Yes, here. Oh, there.
Thank you for your presentation. You mentioned about temporality in graph database. So
yeah.
I was wondering, how do you maintain the temporality in a graph database? Is it property of a graph, or you create a different graph to maintain it?
There are special indices for temporal databases and for spatial databases that you need to build. We don't have any of those implemented. If we need to implement temporal indices, we will do so. So you need to set aside some part of your memory to store those indices and build them. I'll give you a naive example, right? So the geo indices, the ones that are dealing about the world, they are taking, it's called the S2 index. It takes the word and defines it into 6 regions, and those are the first 3 bits of the data. Then each of those squares of Earth is divided in 4, and those are 2 more bits, and each of those is divided in 4 again, and so on and so forth. And that's how you model data in an S2 index up to centimeter squares on the surface of the Earth as a vector coming from the center of the Earth with a structure that you can use bit masking to understand the level of granularity in that. So for time series is a similar thing. Time has years and dates, and you can easily quantify it and create the indices such that you can zoom in and out of that structure. Those are indices that you have to build if you start to operate in those domains, and we'll figure out if we get into that, we'll build them. But we don't have anything right now. There was another question here in the front.
Thanks. I just wanted to ask, I was wondering, as maybe like a software architect or someone who does decisions in the design phase, where is the, like, or how can you tell that the system needs a graph database? Like, and this is maybe in some sense a very basic question, but like where was the moment where LinkedIn or maybe Microsoft was able to say, okay, now we know that graph database is something that we would really utilize and it would give us these advantages over like traditional databases?
So if you go to the slide, I'm not going to go back, but if you remember the 2 columns that crossed each other, if all your data is like that, if everything is a foreign key somewhere else, if the relationships are more important than the rows in the tables, then you need a graph database. So that's kind of the workload that the more you want to traverse, the farther you want to traverse between these tables, then you need a graph database. So if you want to scan all the employees and find what the average salary is, you're just confined into that table. You don't need a graph database. If you want to understand how a storm is going to impact your logistics chain, in the example that I gave with the British Petroleum, then you need a graph database, because you need to be able to model and reason about all those tables, all those relationships at the same time.
2 quick questions. Do you also hire interns? And the second one is, you made a comment about knowledge, something like people are using knowledge, they claim that they're using knowledge graphs, but they're actually using knowledge bases and including some taxonomy on that. Mm-hmm. Can you elaborate on that a little bit?
Yes, so on the interns, we will talk to Subro in the back, or talk to us after this. And in terms of, so I'll give the example of, if you don't have a reasoner, a logic reasoner, something that will take the query and will write the query for you based on the understanding of the world on the ontologies, then you don't need a knowledge graph. It's, people are thoughtful about their schema, they're thoughtful about how they define it, but do they hire 20 ontologists? Do they hire a linguist to implement a reasoner? They usually don't. It's good to have an effort. It's good to have the effort of designing a clean schema, because you don't want to store age. You want to store date of birth, because the moment you store age, you need to know when you store the age, because next year my age is going to change. I don't want it, but it happens. But if you store age, if you don't design your schema well, then you will store data in a way in which is not, you cannot compute the right thing. It's not logical. But do I need an ontologist to figure this thing out? Probably not. I just need somebody that has, right? Reasoning and ontologies are a specialist domain, and they are magical to work with. But no company manages to work so deeply in that. I mean, probably companies that are doing life sciences, folding proteins, that's where you have modeling of digital twins that are closer to ontologies. Those applications would use this thing. LinkedIn, for example, doesn't need a very deep ontology because the schema is very simple.
So you think the reason is because they don't need it, or is it because they are not working professional and is design-wise taking that care into that system?
I mean, my whole presentation has been about pragmatism and practicality. Okay. People don't spend money where they don't need to spend money. So if it's necessary, then yes, go ahead and use a knowledge graph. Otherwise, the organization is going to figure out that they don't want to fund that.
Okay, thank you very much.
So one curiosity, actually. So you show some very nice pictures of graphs. Are you visualizing these graphs in any way? Are you using visualizations for anything?
Visualization is useful in two different cases. It's useful for when you start interacting with the data, and when you really want deep insight into a given constellation. But seeing galaxies on screen is not very useful. More than 1,000 edges are very difficult to observe. There is that common sense that more than 3 concepts in a presentation are very hard to parse, right? And that's how humans work. If you put 100, I've seen presentation with people visualizing graphs. Most of the time what they do is they wiggle with where the data is on screen. Not very productive, not very useful. So I'm skeptical about the usefulness of general graph visualization platforms. Specific ones, they're very useful.
Thank you.
But that's my philosophy, right? So that was that's not a company position.
Okay, mine is a more practical question, maybe. I'm in my second year on the Bachelor on Informatics Engineering here in the university, and well, this seems pretty interesting to me. So, which skills should I try to acquire? Where should I orient my career to do things in this field?
Distributed systems, right? So the big data keeps on getting bigger. Right, so there is no single machine that will be able to do processing on a single machine. So distributed system is a place where there is never enough talent. So divide and conquer, right? And with distributed system comes algorithm. How do you parallelize an algorithm? How do you partition that data into different? How do you do the divide and conquer basically in the system? And my mind is already going. Shared nothing distributed system. You need to put the computation in one places. The shared memory systems are passing control from one computation node to another. So distributed system is always a domain in which it's good to work. You are all probably computer scientists, right? What I discovered, I'm coming from a former communist country. Physics has been the best thing that happened to me, not mathematics. Understanding physics and understanding the world and being able to take learnings from physics and understanding how systems work how life works, right? So all the systems are an approximation, better or worse, of a system that's alive. And I mean, biology will do the same thing, but physics is probably a better proxy.
Okay, thank you very much.
Sorry, related with a question about the visualization, can you elaborate some examples about the data science or analytics behind graph databases? I can imagine something related like recommendation systems or something, but I want to know if there are some other kind of analysis that we can do with that kind of database.
So this is more about how do you, once you discover some insights, how do you present it?
Yes.
Right, so I had some of those images that I had of a very large graph. You know, you apply color, you apply the categories in a way in which is visible, right? So color is one good way. Zooming in and showing people, you know, a planarization of that structure is another way of showing things. I don't know if this is answering the question.
It's more related that, for example, in relational databases, we can have some kind of information to build models, for example, in statistical way, like regressions or trees or whatever. But in terms of that, here in this kind of database, the relations are more important than the properties on each node, for example. What kind of these models or something statistical way we can
So I think
develop?
I'll go back to that slide, because when we were talking, okay. Oh, here. So these are relational tables, right? So the properties are somewhere else, and the you know, whether you represent it one way. So this is an ER diagram, right? So this is how a you know, a portion of an ER diagram is. That is a graph. Whether you use one or the other, it depends more on your user than on the person that is drawing that, right? So a relational database expert is going to like to look at this because they are familiar with that. If you show that information to somebody who's designing ER diagrams for a database, they're going to be confused because they don't understand. You have to get them the information. Habit is probably more important than, you know, you give somebody a representation that they like, and you let them become an expert in it, and they will want more of it, right? But if you take that image and you put 1,000 nodes, nobody's going to be able to understand 1,000 nodes at once. It's like you're giving them a big bag of coins, and you're telling them to pick the 1 or 2 euro coins in a bag of change. Yeah.
So whatever they do is always oriented to that.
Yeah.
And when you try to introduce them to graphs, the paradigm changes.
Get that.
Gracias. So the paradigm changes, and it's difficult for them. It takes them time. I think that this is one of the reasons why graphs have been so slow to take up in the computing community, right?
Yeah. And now, you know, now you have a different set of databases, which are vector databases, which are comparison of vectors, you know, angles between vectors in n-dimensional domains. And if you think of it, you know, what those are good at is telling you how big the angle is between two different vectors if they were rooted in the same place. Can a graph database solve that? No, it's a different index. It's a different purpose of that. A geo database can, you know, IR systems do a certain amount of that. But it's yet a different representation of reality for a given specific purpose.
So let's say I work at a graph database startup. What are some problems Fabric did not choose to solve? Like missing tools or use cases?
I'll use one example, right? Because there was one company that started 4 or 5 years ago, was called Katana Graph. It was trying to push the compute from CPU to GPU, right? Because they wanted to enhance computation. So from that point of view, if you go to that, am I close to a Rubik cube? If you look at this cube, they decided to focus here, right? And it's, you know, this is a product decision, and this is how businesses are built. Somebody's looking at that and is going around the economy and saying, if the economy goes in this direction, I can make $50 million a year by building something there, right? Then you hire a salesperson and say, can you sell this to, you know, what are the Fortune 500 companies that will pay for this? right? And then you go and build something. So they will, you know, if you're going into any organization, they will work on something that's profitable to them, right? In the same way that, you know, if you try to build shoes, you're going to discover that, you know, they're not very comfortable, so you better buy shoes from somebody that knows how to build them. So you decide, you know, you define a taxonomy of what the systems are, you look at the market and you figure out where the money is, and then you start working there, right? Because either the industry is going to get to where you're building a product in the number of years that it takes you to build that. And I'll give you another example because it's a very good, that's not related to graph databases. There are two ways to build an electric car, right? Either you build a Toyota Prius, which is a tiny car with a little car engine, or you start building a Tesla by building a Roadster. You see, one of them has started building electric cars from the hippie community, and the other one has started building electric cars from the super rich community. Strategy, right?
Now that AI is so trendy, how are you linking this with AI?
Graph systems are very good at providing factual answers. If you start using LLMs, LLMs are very good at giving you a statistical answer on past information. So they will be able to tell you common sense information, like what is the temperature that water boils, right? It gets, this information is non-controversial. What is the country that Barack Obama was born in? It gets controversial, and it gets controversial not because it is controversial, because there are more facts that are created in different places where the statistical answer that a large language model learns is not accurate. Now, if you want to go from here to home, and there's been an accident in the subway and you need to take the subway, you need fresh factual data to know how you're going to avoid that. No LLMs is going to be able to give that information to you, because the information is going to be 2 years old and it's going to be statistical. It's going to have a union of all the accidents that happen in the system over the years. It might tell you which is the line that is least maintained, right, if there is something like this. So grounding LLMs and machine learning into factual information is done with knowledge bases or knowledge graphs. As soon as you can teach the machine to reason, you know, and reasoning being a logical thing, it's something that can be learned. You can ask the machine to write a query. You can collect the data about fresh databases into a graph database and answer questions that way. So that's where I think the systems should be going. It's very good at, graph databases are very good at avoiding hallucinations. There's a paper by Larry Hack that has, last year or 2 years ago, that has, you know, a good understanding of how, a good taxonomy, if you wish, of how these systems are built. He's describing common sense and factual information and how to combine these systems into
you mentioned at the start of your presentation a case study with the customer 360. So I want to know more about that. Like what sort of data did you collect to make that 360-degree view, and how did you integrate those data sources, and what sort of role did graphs play in this?
A customer 360 is just like LinkedIn. You know, there's no magic other than that, right? So you have different actors that are consuming that data set. You have clients interacting with their bank, right? So you have bank transactions that happen in accounts. So there's an account table that you have. There's maybe a mortgage table. What unites those things are customer ID. If you take, you know, I'll take another example. You know, Tata, the Indian company, has 300 brands. What they want is people that are using 3 brands to start using 6 brands, 7 brands, 10 brands. So their interest is in combining those data sets and saying, this pattern of usage, we should encourage people to use more, right? So that's customer 360. They are, all these companies that have clients and accounts, they have customer service. So people are calling or they're using apps, they're filing complaints. You need to track how those complaints relate to the accounts and the rows in the tables and how they are solved. All right, so that's another example of customer 360. That's on the company producing the data and managing it. On the consumer end, they build an app and they want you to have access to the app and to your accounts, and they give you a login and identity, and you go and you traverse your data. You look at the profile about your data in their accounts. But, did I build the customer 360? No, there was the idea is what is the segment of the market that we were talking about. Mm-hmm. No, that's good. That's good. Yeah. Mm-hmm.
So you talked about in graph analytics, it's good for factual answers. And if there's a new thing that pops up and it is a node in a graph, can it somehow link with other nodes with an edge to get analytics of that?
Yes, you need to, in most analytics systems, take a snapshot of the world at a certain time, and then they run queries on top of it. You can have streaming graphs where you can collect fresh data and you can overlay it on top of an existing graph. So for example, you have sensor data coming from air conditioning, and it says, the temperature in 5 rooms is, I'm not going to speak Fahrenheit, 26 Celsius, right? So the rooms are very hot. And then you say, how is the data modeled in the building? What is the AC system? What are the edges? Are these 5 rooms connected to the same ventilation system, right? So that's a graph query that you can take fresh data and do a query towards a fixed graph.
Okay, and is there a feedback system involved? Like, can it learn from the previous outcomes and do one thing for the newer one?
Yeah. So all these systems, I mean, you can always layer things on top of them. Are they baked into that's the level of abstraction that I was talking to you in the last slide. If you combine all the things in one, it's going to be very hard to take apart and fix it. Right, so if I put everything into a single database, into a single system, then if I have a new system, then it's going to be, okay, how do I rip apart that thing from inside the system and bring a new one? If you layer it and if you allow these tools to interact, then you can build a tool that does this inference, right? Because I'm assuming that inference is, you can bring the data to the inference machines, you can do the inference, and you can produce the result. So you layer things in a stack. Right, that's why whenever I was talking about reasoning being logical and inference being statistical, that's why I was talking that you put it at the top of the system, right? You don't bake it inside the database, because then, as the domains evolve, it's very hard to mix and match the tool set that you need.
Thank you.
No, ask it and then pass it along. You have it.
Okay.
Possession is 90% of the game.
Okay.
You got it. Speak up.
So, in the semantic data management course here, we're using Neo4j as our technology for graph databases. And I was wondering, because it sounds like you guys at LinkedIn and Microsoft have your own technology that you're developing. So what are some of the ideas that you are developing that are not really seen elsewhere in something like Neo4j?
First off, we have to start providing universities with free copies of the system, such that people learn how to use them, right? So that's a very good point that you have there. The systems and the concepts are similar in the two systems, right? So Neo4j has similar analytics tool where you can create, you model a graph, you create it, it stores it as a database, so the big difference is we are an index, they are a database. It provides algorithms, so the ability to systematically run over the data. They are a scale-up system. We are a scale-out system. They are paging the data on disk. The liquid index is entirely in memory. So these are the fundamentals. So scale out, scale up is the more important, you know, the different, and the fact that they are a database and we're an index.
Thank you. Well, my question is an extension of LLM model in graph database. I was wondering, we already have RAG system, which is retrieval augmented generation, to avoid the hallucination or reduce the hallucination using vector database. I was wondering whether graph database is practically implemented to reduce those hallucination, or it is just a theoretically available, or
there is hundreds of papers in the last year or so about that. RAG systems are still IR systems, right? You don't get a precise answer, you get a ranked answer. So if you have 3 conflicting results about where's the traffic in the system, then you're gonna have to decide by yourself, you know, which one is actually the accident and which one is not. So RAG systems are generally using vector databases for the, can you build a vector index on top of a graph database? Yes, but it's not very interesting because the dimensionality is different, right? So it's better to use the right tool for the right thing. Where the systems will evolve, you know, it's too much to speculate in, right? So there is no single, you know, there is no single tool that will solve all of them.
Thank you.
So the same way that in distributed systems there are 2 problems, well, 2 main problems, exactly one's delivery, guaranteed order of messages, and exactly one's delivery. What are the main problems in graph databases? Or
so we are using distributed systems, right? So exactly one's processing is interesting for us as well. Consistency is one of the biggest problem in distributed graph. When you're appending the graph with data, the data can come in different orders, right? And that's the problem with temporal systems, right? So you can reason over graphs in a temporal way, but the order in which the data comes is not necessarily the order in which the data is produced. If you're distributing data, if you don't have global IDs, then you don't know which, you know, some shards are faster, some shards are slower. So if you're trying to produce a result as of a given date, then you need that time to be consistent across all the shards. So, you know, data, you have technical problems at the consumption of the data and how do you make the system consistent. You have problems at the producing of the results and how do you produce consistent results. Now, if you have replication, there's another problem of how do you make sure that each replica is consistent with the other replicas, right? So if you ask 2 different systems the same question, are they going to give you the same result? All of these are distributed system problems. Query planning, query execution in distributed system, you know, how do you partition a graph in such a way that you can answer the question the fastest way? Because if the query has a long diameter in the graph, so it has many hops in that ball and stick diagram that you can imagine, you have to partition it and send it back and forth in a query processing model to the system multiple times. How you cut that graph has relevance in how fast and how efficient you're using the compute. Because if you're inefficient, then you might be able to traverse the entire graph watching it. Right? So imagine world contains countries, contains regions, contains villages, contains parcels. Right? If you drop the coin and you're trying to figure out where that coin is, you better the coin up because there is only one, you know, the edge. There is only one edge that says contained by. If you look from the contained in, then you're going to traverse the whole world to scan and to find the coin.
And a super quick question. You said that in LinkedIn, like this liquid, it's an index, it's not a database. So does it mean that there is an underlying database that from the index, it points to that database, or like?
So the term that people are using is source of truth, right? So traditionally, the source of truth is the first place where the data is stored. Right, and everything else is a replica, or is an index, or is a materialized index, or is a view, and so on and so forth. If you're forcing organizations to change the way they operate, right, then you're asking them to change the way they're organized. Right, so all of a sudden, you're not selling somebody a tool, but you're telling them how they should arrange their apartment, and they don't like it. Right, because they run their own family and they don't want, right? So having the organization stay as it was, it's much easier. And if you're not creating materialized views or copies or ETL, you're not creating copies of the data that are stored on disk and they are stale. So having an index that is always live means that the moment you unplug the graph system, the data doesn't exist anymore.
But then how is the source of truth stored?
They're the relational databases in general.
Okay.
So again, you know, this is all about practicality. No system will replace another one. You know, you will add new systems as you need them, right? I mean, if you bought knives, when you buy a new knife, you buy a new knife because either you throw the old one, right, and you're replacing a knife, or because you need a different function and you need a specialized tool. So the graph databases are not going to replace the relational databases. They're going to complement. You have different functions for different things.
Thank you.
Two questions. When it comes to data, scalability is an issue. So what specific challenge did you face when you were scaling your graph database, and how did you overcome it? And secondly, what technological stack did you find most effective as you were building your graph database for both LinkedIn and Microsoft?
Stability is very loaded, so I don't know what you mean by stability, because scalability. I mean, the problem with scalability is scale up and out, right? And I will comment from the perspective of two different companies. When you are building a bespoke system for a single client, you can choose the best hardware that fits the need, right? And that was LinkedIn. We built the system. We decided which hardware we're going to use. We bought that hardware, and we installed it in our data center, and we used it. When you're developing systems for the enterprise, then you're relying on what hardware is available in the data center, what hardware is available in 10 data centers if your client is going to be geographically distributed, right? And data center A and data center B might have different families of hardware. And what hardware is the client willing to pay for? Right? There are people that are very cost conscious. They only want to buy 64 gig machines. There are people that are willing to buy 2 terabyte of RAM machines. Right? If you take these three and you try to design the system for one of them, you're going to discover that the set intersection of that is 0. Right? So you have to become pragmatic, and you say, oh, you know, I will build my system on CPU but not GPU, because all the data centers are based on GPU. If you make the decision that you're going to build it with GPU and the GPUs are going to be a requirement, then what you're going to discover is that the people that are building AI systems are much more willing to pay for the GPU than the people that are not using AI systems. So there's going to be a shortage of GPU. Right? So the practicality is going to be that if I decide to build a GPU-based system, I'm not going to be able to source the machines necessary to deploy it. Right? So it's supply and demand. What was the second part? Oh, the tech stack. The tech stack is usually decided by the company, not by the technologists. For example, we developed C++ at LinkedIn in a Java house. That means that if you do that, it means all your technical C++ stack is yours. It also means that you don't have to deal with garbage collection. And I think it's worth it. right? So garbage collection is extremely good for a system that is not operational, right? You have GC pauses of 2-3 seconds in one system at random. Would you like for your LinkedIn profile to load in a minute once a week? Okay. So it's practicality. But in general, if you think, oh, I will go to this company and I will develop in Haskell, it's not going to happen. You know, unless the company develops in Haskell or in Linda, you know, you can take your talent there because they need your talent. If you have knowledge about graphs and you're coming and say, oh, you know, I can develop this thing in Haskell, in order for me as a manager, right, and I'm not talking as an engineer, I'm talking as a manager right now, is I have to find 4 more Haskell engineers. Oops. Right, so it's all a matter of practicality. Thank you. Thank you all. I really appreciate it. Thank you.
So I have a quick